let's talk about buoyance forces. Chunk number 2 of this. Sorry, I forgot to hit record. So when we talk about chunk number 2, we're going to be dealing with forces. So we want to spend a little bit of time talking about some forces from previous unit of forces, Newton's second law, and force of gravity. But the big one we're going to talk about is buoyancy. So when we talk about buoyancy, buoyancy is a force, and it's a force that is upwards when it is immersed in a fluid. So anytime an object is immersed in a fluid, there's an upward buoyant force. So we talk about throwing a block of water, a block of wood on the water is going to float because there's an upward buoyant force. If we take a hunk of steel, we throw in the water, it's going to sink, but there still is a buoyant force that's going to act upwards. And I kind of lied to you. This is where you guys are picking up again. I kind of lied to you back in our free body diagrams of forces, and you say, if I'm standing here on the ground, what forces are acting on me? I said a normal force and a force of gravity, and those are the two forces. Kind of lied, because technically there is a buoyant force, because anytime an object is immersed in a fluid, and air is a fluid, there's an upward buoyant force. It's just really, really small, so it's pretty, we just kind of ignore it. But technically there is. So most of the time when we talk about buoyant forces, we're talking about water or salt water. Those are typically the two fluids. Sometimes we'll talk about maybe, say, a hot air balloon. Then the fluid the hot air balloon is immersed in is air. We could talk about a helium balloon, and the helium balloon is immersed in air. So then we'd have to talk about the fluid being air, but most of the time we're going to talk about water or salt water. So let's quick kind of talk forces stuff from last semester, which I know was a long time ago, and I know forces was one of our tougher units. So on the front of our formula sheet, we have our forces. However, the two force equations that we're going to use, I also repeated them in our fluid section right here, and I have them written on the board. So let's quickly talk about Newton's second law. So Newton's second law says the sum of all my forces is equal to F net, which is equal to mass times acceleration. So that is true for both the x and the y direction. And when we talk about that, we talk about the acceleration. And we talk about if the velocity is constant, then my acceleration is 0, which means my F net is 0, which means my forces are balanced. If my acceleration is not 0, all that other stuff. Very conveniently, with buoyant forces, things are floating on the surface, they are sunk to the bottom, or they're being held in place somewhere in between. And in all those situations, my velocity was constant, which makes my acceleration 0. So most of the time, I think I can make the statement all the time in this unit, I think. But maybe I should say most of the time, the velocity is going to be constant, which means my acceleration will be 0 in this particular unit. And we technically have to do the sum of all my forces in both the x and the y, but because we're talking about things sitting on like the surface of water, we're really only talking about the y direction. So when we sum up all of our forces, we're adding our ups and we subtract our downs. I've said that kind of add your ups, subtract your downs, add your rights, subtract your lefts, but we're only dealing with the y direction. Okay, so that's kind of our quick review on forces. When we talk about buoyant force, I'll define all those things in there, which I already have written down there, but I'll talk about that in a second. When we talk about things floating in a surface, floating in a fluid, the very quick and easy way to describe why an object will float or sink in a fluid is just straight density. So if I take a block of wood, like a pine board, and I throw it in the water, it's going to float. And the reason why that board floats in the water is because the wood is less dense than the wall. If I take a hunk of steel and I throw in the water, it sinks. Like a boat anchor, right? Throw a hunk of steel in the water, it sinks because it's more dense than water. That's the quick and easy reason why things float and sink. But that only works for solid objects, uniform solid objects. Because it is possible to make a hunk of steel float, or a hunk of aluminum float, even though the density is higher. And you can say, really? Yeah, they make ships out of steel. They make fishing boats out of aluminum. Okay? So why can they make those things that are more dense float in water? It's not because of the density, it's because they're able to displace enough water to make it float. There's a big enough buoyant force acting on it that it can float. The quick and kind of easy, well, I shouldn't say quick and easy. In order to determine whether something is going to float or sink, you'd have to look at how much fluid they're going to displace. So in chemistry last time you took it, and whether it was a sophomore or junior, you had those little cans, we've referenced this before, they had those little side arms on it, and you had the balances and weights and the green and yellow fluids, and you put that weight in there, and the water level would rise, and it drain out, and you collect all the water and make a big mess. The idea is if you had a 100-gram weight, and you collected all the water, if the amount of water displaced was equal to 100 grams, that object would float. Okay? But in that case of steel, it doesn't. So if an object displaces its weight in that fluid, it will float. So for example, a 100-pound aluminum fishing boat. I don't even know if they make a 100-pound boat, but whatever. Take a 100-pound aluminum fishing boat and you put it in the water. When you put that boat in the water, just like Archimedes said in his bathtub thing situation, when he climbed in the bathtub, the water level went up, and he realized that, hey, I, in the bathtub, am displacing a certain amount, a certain volume of water. Same thing happens when I take my aluminum fishing boat and I place it in the water. The water level of the lake rises. Now, we're talking generally big lakes, so we don't notice the rise, but technically every time something else goes in the water, the lake level increases. Every time you take a stone out of it, it drops a little bit. So what's happening is if you were to put that 100-pound fishing boat in the water and you had a giant overflow can, kind of like you did in chemistry, or like a perfectly flat lake with a dam that like the water was right on the brim, and then you set that boat in, the water level of the lake would rise and it'd go over the dam, and if you collected all that water and you weighed it, 100-pound boat, if it floats, will displace 100 pounds of water. And what happens if you put another 100 pounds in it? The boat's going to sink further down, the lake level's going to go up, and it'll displace some more water. Okay, so they talk about displacement of the fluid. This is our force equation for buoyant force. Okay, so it's my buoyant force equation. It's on your formula sheet. So buoyant force, all forces we've dealt with, we calculate things in newtons. So the buoyant force is equal to the density being displaced times the volume being displaced times the gravitational acceleration. Okay, G simply, we're on Earth, 9.8 meters per second squared. These two I kind of put some descriptors by to try to help clarify some of this. This is the Greek letter rho, represents density, and it's the density of the fluid that's being displaced. It's the density of the fluid that is being displaced, and our units are kilograms per cubic meter. Most of the time, the fluid that is being displaced is water or salt water. So most of the time, that is going to be the density of water. The question you kind of ask yourself is, like, if I take a hunk of steel and I put it in water, does the steel push steel out of the way? Did it displace the steel? Did the steel displace the steel? Or did the steel push water out of the way? Did the steel push the water out of the way? And if the answer is it pushes water out of the way, which is kind of hopefully clear, then this is going to be the density of water. This is the volume of the fluid that's being displaced. So when I talk about putting that 100-pound boat in the water, it's going to push a certain volume out of the way. But it's not going to be completely underwater. But once I put more weight in that boat, it's going to sink further in the water and it's going to push more water out of the way. So this is always, the way in my mind, I don't write it like this, but I'm thinking that's the amount of volume that's underneath the water. It's how much of it is in the water or in the fluid. And again, times G, and that will give us our buoyant force. So when we talk about volume, a lot of times we're going to talk about these nice cube-shaped objects, and I say cube very generically. It's not really cubes. We typically deal with rectangular prisms, would be the official term. Because a cube is all three equal sides. So when we talk about rectangular prisms, it's a cube-like shape, but they aren't all equal. So on that sheet that I asked you to pick up called in-class buoyancy, we're going to go through problems number 1 and 2, which there's an A and B. But pictures are going to be helpful, and labeling our pictures both with forces and with dimensions is also going to be helpful. So there's my not great three-dimensional rectangular prism. I can do better, and I probably should. Now I don't know if that's any better. But whatever, I have a rectangular prism, cube-like structure, and according to the information, it says A block with a density of 650 cubic meters per kilograms per cubic meter is floating in fresh water. The dimension of the block are 0.25 meters long by 0.15 meters long and 0.1 meters high. And the density of H2O is 1,000. So I'm going to label the dimensions. My block is 0.25 meters long by 0.15 meters wide by 0.1 meters tall. Now, I'm going to say this, that I chose this to be my length and this to be my width, but they very easily could be flipped. Doesn't matter. The thing that is important is it says I have a height of 0.1, and that is an important dimension to keep straight. And it's going to be put in water. The question that I'm asking us to solve for is how far under the water will this thing be? So it's 650 kilograms per cubic meter in water. Water has a density of 1,000, so therefore it's a block, it's less dense, it's going to float. So my blue kind of squiggly line is to try to show you the water level of the block. And the question being asked here is, what is my H? How far underneath the water is that object? Now, over in our buoyancy equation, one of the variables was the volume that's being displaced. And I said I like to think about that is how much of the block is underneath the water. So I'm going to use a yellow marker, which is not a very easy marker to see, I understand, but I'm just trying to use it for like shading to say, hey, the yellow shaded section is the amount that's underneath the surface of the water. So when I talk about in my equation the volume that's being displaced, how much of my block is underwater, I'm talking only about the yellow shaded portion. I'm not talking about the whole portion of the block, I'm only talking about the yellow shaded portion. So in order to calculate the height, to solve for that H, in the buoyant force equation for the volume being displaced, it's the three dimensions because it's a rectangular prism, it's length times width times height. It's my length times my width times my H that's under the water, and only underwater because it's the volume that's being displaced. That's where that's going to come in. We're going to solve for that dimension in my volume that's being displaced equation in this particular problem. So now when we start looking at this, we start thinking, okay, so this is a forces problem because there's a buoyant force. It's immersed in a fluid, therefore my buoyant force is going to be up. I don't know if I mentioned this, your buoyant force is always going to be straight up. Yeah, your buoyant force is always going to be straight up into the air, or straight up, I should say. Then we also have an F of G, because anything that has mass and is on gravitational field is going to have a force of gravity, or a weight, or an mg. Now, in the past, I said, hey, this is a 10 kilogram object, a 15 kilogram object. I've been nice enough just to give you that number, and then we can multiply by 9.8, the mass. I've given you that mass. Back in the first chunk, I talked about I'm not going to be that nice to you, and I'm not going to give you just the mass. However, if we know the density of the block of wood, and I can calculate the volume of my block of wood, I can then solve for the mass of my block of wood. Now, this is when we talk about the density of the block, it's the entire density of the block. When we use the volume, it's going to be the entire volume of the block, which is going to give me the total mass of my block. And I'm just going to kind of say it that way to kind of help emphasize it. So in order to calculate mass, we take the density of the block, 650, and I set that equal to the mass divided by the volume of the block. Now, how do we calculate the total volume of the block? It's the total volume because it's the total mass, the total density is going to be my length, 0.25, times my width, 0.15, times the H, the entire H of 0.1. And when we go through, cross multiply and divide, 650 times 0.25 times 0.15 times 0.1, we get a mass that is equal to 2.4375 kilograms. So your F of G is simply taking the mass times 9.8. So this is going to be 23.8875. And I'm going to keep all of the decimals just so we don't have the rounding issues yet. There's 4 of them, I can write 4 decimals. So that's my force of gravity. Now, all of that is great except for I don't know my buoyant force, and I don't really, and what I want is H. So the way we get to that is we use Newton's second law. So Newton's second law says the sum of all my forces is equal to F net, which is equal to mass times acceleration. Now this object is floating on the surface, which means the velocity is constant, which means our acceleration is 0, which means my F net is 0, and my forces are going to be balanced. So when I use this over here, those are 0, and when I use Newton's second law, I'm adding my ups, subtracting my downs, and I'm setting equal to m times a, which in this case is equal to 0. So I add all of my ups, there's only one. I subtract all of my downs, there's also only one. I set that equal to m times a, which is 0 because my forces are balanced. I am gonna be solving for h within this part of my buoyant force equation. So I'm just telling you in advance, I am gonna wanna isolate my F of B by itself. So I get a little lazy sometimes, and your math teacher probably would approve of this stuff if you're supposed to be showing your work. But since this is a minus FG is equal to 0, if I wanna move this to the other side, what do I do to get FG to the other side? I add it, which means, right, it's not officially not right, but I did. I added FG to the other side. I just saved myself a one. Okay. So my buoyant force equation is the density of the fluid that's being displaced. What is the block pushing out of the way? Is it pushing the block out of the way, or is it pushing water out of the way? What's the fluid that's pushing out of the way? Water. Good. So that's going to be the density of water. And then it's times the volume that's being displaced. And again, it's only the shaded yellow sections. So it's the length that's under the water, times the width that's under the water, times my height that's under the water. So I'm gonna take my density of water times length, I'm using cursive value just so it doesn't look like 1, times my width, times my h, which is our unknown that we're going to be solving for. That's where that's coming from. That's what we're solving for. And don't forget to multiply by gravitational acceleration. That's an easy thing to forget sometimes. I forgot yesterday to do it. And that's all equal to F of G. We can start plugging numbers in. The density of water is 1,000. The length of my block is 0.25. The length of my block is 0.15. The height of my block is h. That's what we're solving for. G on Earth, 9.8 meters per second. And our F of G, we already calculated it to be 23.8875. And we already calculated it. So when we go through and we do the algebra, we take 1,000 times 0.25 times 0.15 times 9.8, don't forget to multiply by 9.8, we get 367.5 times h, which is equal to 23.8875. Divide both sides by 367.5. And my h is 0.065 meters. So what that means is from here to here is 0.065. Just to do a quick check, it needs to be less than 0.1. Right? It's only 0.1 high, so it has to be somewhere between 0 and 0.1. And it is. That's on that calculator. This is a pretty common calculation that I asked you to do, is solve for how far underneath the water. And that how far comes from the volume that's being displaced. And it's the dimensions that are underneath the water. It's a shaded yellow section. Now, this next problem, it's kind of in part B. It's a new calculation, but the wording is such, it's kind of weird. I use the word swamped, but the reason I do that is because on one of your homework problems, I use that same term, so I'm trying to introduce it. But it's the exact same block for part B, so it has the exact same dimensions. It has the dimensions of 0.25, 0.15, and 0.1. I realize my picture's not drawing the perfect scale, but that's okay. It's the same block. Oh, here, let's actually read. How much stuff can be placed on the block before it's swamped? So if this is where my water level was when it was just the block. As I put stuff on it, the water level changes, right? And the more stuff I put on it, the deeper in it's going to go. And what I'm trying to determine is how much stuff, like what's the weight, can I get right before, and I'm using the term swamped, and it kind of is a reference to like a boat. If you swamp your boat, you swamp your kayak, you swamp your canoe, you've gotten the water so close to the level that it's actually starting to come over the sides. So that's what I'm saying. It's just like it's like as high up as it possibly can go. So when we talk about, well, what forces are acting on this block? Well, we have a couple things. There's still the FG of the block. Did the block's weight change? If I set something on top of a block, did the block change? No. Does your car get heavier when you climb into your car? Does your car physically get heavier? No, right? Same idea here. The block itself didn't change. If the block is sitting on a scale, the scale is going to read a different number when I start setting stuff on it. But let's kind of keep that separate. But because I'm setting stuff on it, we have another F of G, and I'm just going to very generically call that FG of stuff. And that's what I'm asking to solve for. How much stuff, what's my F of G, what's the weight of stuff that my object can hold before it gets too deep? And there is going to be a buoyant force. Now, is my buoyant force going to be the same in that one as it was in part A? And we can kind of look at our equation for buoyant force. Did the density of the fluid change? Did I switch fluids? So that's still 1,000. Is the amount of block that's underneath the water change? Yeah. So the volume being displaced changed, therefore the buoyant force is different. We don't know that number, but there is an upward force. Okay, so that's the idea. That's my free body diagram. in order to calculate, can we see this in the video?
Yeah.
Yeah, okay, thank you. I'm just gonna, I'm gonna use Newton's second law, and Newton's second law says the sum of all my forces is equal to F net, which is equal to mass times acceleration, and it's still floating on the surface, therefore my acceleration is still 0. My F net is still 0, therefore my forces are still balanced. That still holds true. But when I do this problem, I add my ups. I add my buoyant force, and that's my only up. I subtract my downs. I subtract my FG of the block, but I subtract all of my downs, so I have to make sure I subtract my FG of my stuff, and because that is not accelerating, we can set that equal to 0. My FG of stuff in red is the variable himself. Now, I'm going to do that kind of quick and lazy math again, because this is what I'm going to solve for. I want to isolate it. I want it on its own side, and I might as well do that right now, because I put it in this order, not by accident. I can just say, hey, that's a minus. I would have to add that to the other side, and once I add it to the other side, it's going to equal FG of the stuff. So it's the same kind of, I'm going to add it. That's what I'm going to solve for. So now let's start plugging in, breaking the equations down. So my FB of the buoyant force says it's the density of the fluid that's being displaced. What is the fluid? It's water. Times the volume that's being displaced. We're going to do this. When we talk about the volume being displaced, it's the shaded yellow section. How much of my block is underwater? That is the dimensions that we need to use. So in this case, it's like right on that verge of being swamped. It's all of the length, it's all of the width, and it is the full height, not the height we just calculated, but the full height of 0.1 is going to be completely underwater. Times G. Don't forget times G. And that's going to be minus FG of the block, which we've already calculated, and that's going to be set equal to FG of our stuff. Density of water, 1,000. Length, 0.25. Width, 0.15. Height, 0.1. It's the dimensions under the water is what we are using for volume being displaced, times G, 9.8, minus 23.8875, which equals FG of the stuff. These times, I think I've memorized this eventually. 1,000 times 0.25 times 0.15 times 0.1 times 9.8. My buoyant force is 0.75 newtons minus 23.8875, which equals FG. So then we take those two numbers, we subtract them, and our FG. Now I'm going to round at the very end of 12.86 newtons. That block can hold 12.86 newtons before it will swamp or sink, essentially. Okay, so that's a kind of, the reason that question's there is there's a question on your homework that talks about like a canoe and how much stuff can go in your canoe before it's swamped. It's like, it's completely underwater. It's about to go over the edge. That's the intent of that question. Okay, that's how we treat problems that are floating on the surface. Now, if that object were to be sitting on the bottom of the lake, then then there'd be a normal force, right? Because now it's sitting on the lake, it's sitting on a surface. The volume being displaced, how much of it is underwater changes the higher up it goes or the deeper it goes. So if we treat this like, let's think about this as being you. Let's pretend that you were a rectangular prism and you're in water and you are length times width times height. But if you're only ankle deep in the water, you're gonna have a certain buoyant force. But now if this becomes waist deep in water, this number becomes bigger, which means your buoyant force becomes bigger. If you're chin deep in water, your H is bigger, therefore your buoyant force is bigger. The deeper you go, the more of you is in the water, the bigger that buoyant force. So, this summer you're at the lake, you're ankle deep in water, your friend is ankle deep in water, you go grab him and try to pick him up. It's gonna be pretty close to picking them up as if they were standing on this floor, because there's only a very small buoyant force, because this H is really small. If they're waist deep, it's easier to pick them up, because they're waist deep in water, there's a buoyant force acting from waist deep and down. If they're chin deep, it's easier yet, because they're displacing more water, there's more buoyant force to go. But what happens the higher you lift them up out of the water, the heavier they get. They feel heavier, they don't really change, right? They feel heavier because their buoyant force is going down because they're displacing less water. That's that idea of. Now, why buoyant force is an upward force, and let me just kind of throw this out there just to make sure I say it. The buoyant force is always upwards, and it has to do with the difference in pressure. So if we talk about, like, if I'm standing on the bottom of a swimming pool, the further down I go in the water, the higher the pressure, right? So the pressure at my feet is actually higher than it is at the top of my head. And pressure always flows from high pressure to low pressure. So it's actually kind of pushing upwards and kind of lifting me up. That's where that buoyant force of an upward buoyant force kind of comes from.
So is that why, like, human bodies like float?
It actually has to do with, so kind of, some people don't float.
Really?
Like, some people just don't float very well. And what it has to do with your body composition. So we're relatively a solid object, right? I mean, we're not really uniform, but the idea is it's not like a boat with an air pocket in it, right? So the boat goes down and we're just pushing, this is air. We're filled, we're a filled substance. But let's just say I'm 100 pounds. I'm 100 pounds of just pure muscle. That has a different body composition, or we could just density, than if I was 100 pounds with a lot of fat, right? Those are two different kind of body styles, and based upon that, it essentially changes the density of the person. So you could have two different people, assuming they're the same height, but they could have like be pure muscle or a fluffier person, right? And they would have different buoyancy because they displace different. They would displace different amount. They would probably displace different amounts of water, is what it comes down to. But it's kind of the density. What they often say is they say muscle weighs more than fat, right? You heard that. So the idea is if you were more muscular and had less fat on your body, you need some fat on your body, let's just make sure that's clear for everyone, you probably would float not as well as someone who had more fat percentage of body weight. So that's, and I'm gonna say this, and that's why that your BMI, and I'm sure your health teachers have talked, that's why the BMI isn't a great indicator of stuff, because you could have a person who is like zero, like I'm just some really small percent body fat, but because their weight, they're really strong, it puts their weight at a certain category, they could be considered like obese, even though they're just like, but I'm sure they talked about that in Phi-Ed.
Yeah.
So, but it typically people who are have more fat float better than people who are. The thing that I never understood, and this is just one occurrence. My grandpa claims that when he after he had a stroke, he wouldn't float. Like, he used to like swim and float, but after his stroke, he like sank.
How's that work?
I don't know, and I don't know if, and maybe it has to do with the time he was recovering, he lost so much muscle mass.
Mm.
Maybe, I don't know, I've never actually. That'd be my guess. It was probably a loss of muscle mass. But also, we talk about, I referenced it one other time, there's this, the Dead Sea. It's this really salty body of water in the Middle East, I think it is. You float much better in the Dead Sea because it's really salty. So the density of the fluid being displaced is higher than like, say, Lake Wausau. So because this is no bigger, this is bigger. You float better. Same thing in the ocean. You actually float a little better in the ocean than you do on a lake because the density of the fluid is greater than when you're in the ocean. All right, let's do this last problem, get you set up, because then this should get us hopefully at a good spot for your homework. This is problem number 2 on the in-class worksheet. So this one's a little bit different. Now what we have is we have a 0.01 cubic meter block. That's the volume. Cubic meters is a measure of volume. Remember, that's a cubic meter, meter by meter by meter. And it has a density of 1,200 kilograms per cubic meter and is attached to a string and is suspended in fresh water. If fresh water has a density of 1,000, the block is 1,200, is that gonna float or is that gonna sink? It's more dense than water, so it's gonna sink, right? It will sink. So that's why it has a string to kind of hold it or suspend it, is what they're talking about. So we have this block that is completely, it's completely underwater. The volume of my block, I'm just gonna write it right on there, is 0.01 cubic meters. I don't give you the dimensions, I don't give you length times width times height, I'm just telling you the volume itself. So it's being held in place by a string, otherwise it would sink to the bottom, and if it did sink to the bottom, then there would be a normal force because it's not sitting on the bottom, it's not sitting on the surface, there is no normal force. But because there is a string, there is some tension, and that's what this problem is asking us to solve for. And sometimes people struggle a little bit to say, how do I know which direction the tension is? If I were to cut that with the scissors, it goes, the string is holding in the opposite direction. So if I cut it and it were to sink, my tension goes up. If I were to cut it and the object went up, my tension would be down. You can say, well, it wouldn't work here, but like a helium balloon, don't do this, it'd be really mean. Walk up to a little kid who just got like their helium balloon from some, go snip, it'd be really mean. But then what would happen, the balloon would go up, which means the string was pulling the balloon down. But in this case, this is what we're asking you to solve for. The other forces acting on it, there is the F of G of the block, and because it's immersed in fluid, water, there's gonna be a buoyant force. So those are our 3 forces. Again, I'm not nice enough to give you the mass, so we have to say the density of the block is equal to the mass of the block. This is a pretty common calculation that I ask you to do, times the volume of the block. So the density was 1,200, the mass is our unknown, the volume is 0.01 cubic meters. When you cross, multiply, and divide, we get 12 forces. Then we can use this 12 kilograms to then calculate the F of G. So 12 times 9.8, I think is 117.6. 117.6 units. That's our F of G. Now, there is no magic formula for tension, therefore, I need to use Newton's second law. Newton's second law says the sum of all my forces is equal to F net, which is equal to mass times acceleration. It's being suspended in the water. Suspended means just kind of held in place, which means my velocity is constant, which means my acceleration is 0, which means my F net is equal to 0, which means my forces are going to be balanced. Newton's second law says sum of my forces, I add my ups, so I'm going to add my ups, I'm gonna add my tension, I'm gonna add my ups, my buoyant force, I'm gonna subtract my downs, and that's gonna be set equal to 0. Now, I'm not gonna do the lazy map thing because it doesn't work quite as cleanly right here. You could. I'm solving for a tension. And then I'm gonna add my buoyant force. My buoyant force equation says the density of what's being displaced, the density of the fluid, and this is in water, so the density of water is my fluid, times the volume. How much of my block is underwater? And the answer is all of it. So the volume being displaced is the total volume of the block because all of the block is underwater. Don't forget to multiply by G. And that's minus f of G, which is equal to 0. And we already solved for f of G of block, that's why I left it like that. We could just say m times G if we really wanted to. Ft, tension, is 1,000 times 0.01 times 9.8 minus my f of G of the block, which we calculated to be 117.6. 1,000 times 0.01 times 9.8 is 98. Okay, so my f of T plus 98 minus 117.6 is equal to 0. I gotta move this to the other side, I have to add it, I have to move this to the other side, I have to subtract. So 117.6 minus 98 gives us a tension, an F of T of 19.6. Okay, so that's my F of T. That's kind of the problem that we're going to kind of get to today. I do want to get you, because I know you'd be disappointed otherwise, I want to get you a homework sheet for you to work on. This homework sheet has a front and back. This is once again going to be one of the homework sheets. I'm going to ask you to do the front and then wait on the back. So there's nothing for you to submit as of right now, but these problems on the front are similar to the problems we did. How deep in the fluid is it? Then there's a number 2, if we take a quick look at number 2. Number 2 talks about 2 people, 2 paddlers. We're talking about a canoe, so a paddler is a person. There's 2 people who climb onto a canoe. Now you can treat that as 2 different things. You could say the people have an F of G, the canoe has a separate F of G, or you can say like when you climb in your car, you and your car kind of have a F of G, and that's fine too. So part A is how far in the water is it with the people, and then part B is how much stuff, gear, can they put in until it's swamped, okay? And then there's another problem with a block on the swim. So those the problems I want you to get started on. I'd like you to have those done for your next in-person class, and then we'll work on the back, and once we finish the back, then we will submit the homework.